much. Thank you very much for coming. So yeah, I'm Masaki Oshikawa from University of Tokyo, and I'm always happy to come back to this paradise for theoretical physicists. So I'd like to also thank all the staff at the Aspen Center for Physics for running this wonderful place for many years. So yeah, also it's a great honor to speak for this colloquium. So yeah, I see many in the audience from our community, quantum many-body problems, and probably I will mostly discuss something you already know well. But this colloquium is supposed to be, introductory for people in other fields. So please excuse me for this. So yeah, my talk title is thought experiments on quantum matter. And I think I'm supposed to, so first, what is thought experiment? So physics may be divided into experimental and theoretical physics. Of course, that boundary is not always clear, which is a nice thing. But I'm theorist, so I'm mostly going to talk about theoretical physics. And typically, theoretical physics start from modeling of physical phenomena, material, and then we try to formulate this model in mathematical way, and then we do some calculation, some computer simulation, and we get to some predictions, and we compare this prediction with experiment, and get the feedback, maybe modify this model, so on and so on. Now also, once we formulate a model in mathematical terms, then the problem is in some sense reduced to mathematics. So maybe we can ask mathematician or mathematically very fluent colleague to, prove some theorem or do whatever. And yeah, this mathematical analysis is very important, for example, in classification of topological phases. Okay, so this is roughly what we do. But I think there is another aspect, element of theoretical physics, which I like very much, which is this thought experiments. I'm not sure where to put this thought experiment in this diagram, so I just put it here. But for me, this is at least one of the best part of theoretical physics. And actually, I think the history of thought experiments is as old as the history of modern physics. So, for example, if you go back to the very fundamental problem of falling objects. In very old times, for example, Aristotle and people at that time thought that the heavier object should fall faster, which looked reasonable for our daily experience. So apparently, this idea stuck for centuries or even thousands of years, until 16th century, when one of the fathers of modern physics, who is Galileo Galilei, came up with a brilliant idea. That is, he asked a very simple question. What happens if you connect these two objects? According to Aristotle, this heavier object should fall faster, and the lighter object should fall slower. And if you connect these two, and this heavier object should be dragged back by the lighter object. So in total, this combined object should fall maybe at the speed in between these two speeds. So it should be definitely slower than original falling velocity of the heavy object. But on the other hand, once you if you connect these two objects, and you can regard these two objects, connected objects, as a single object, which is heavier than each of these objects. And total objects should fall faster, even faster. So you can already see the contradiction in this very old Aristotle idea. So I would say this is very brilliant. Of course, Galileo didn't just do this thought experiment. He did a real experiment, measurement, and so on, so on. That's why he was great. But from this, you can already see the power of thought experiment. You don't have to do any experiment. You do this experiment only in your head. But still, you can say something very useful. And so this is very typical or characteristic for thought experiment, because by doing this very simple thought experiment, you cannot predict how fast this object should fall. But still, you can show the contradiction of some theory or some idea, which can be very powerful. And then in history of physics, there are many other thought experiments which actually played a very key role in development theory, including Einstein's relativity. What if you try to observe the acceleration within the spaceship, also Schrödinger's cat, and the Maxwell's demon in StatMech, and so on. But today I want to apply this thought experiment approach to quantum many-body problem, condensed matter physics. So in condensed matter physics, we deal with enormous number of electrons in solid, and they move and interact quantum mechanically. So then if you want to try this by brute force, you try to diagonalize a huge Hamiltonian whose dimensional Hilbert space is given by exponential of this huge number, which is of course totally intractable. So you cannot really directly simulate this in very faithful or brute force manner. But of course, over many decades, theorists have developed various theoretical and computational approach, like perturbation theory, computer simulation, DFT, quantum manifold, DMRG, and so on. And in simulation, typically computers handle only a finite size system, but we can try to extrapolate this finite size result to some like limit or infinite system size. So there are many progress, but still this kind of problem is challenging in general. Then maybe more modern take approach to this kind of problem is as follows. We want to understand the microscopic model, but then we cannot directly, it's very difficult to handle these microscopic models directly. But on the other hand, we are usually interested in macroscopic behavior, property of this material or model. So we try to develop low energy effective theory. And the nice point is that this low energy effective theory can describe universal phenomena, and also it can be actually asymptotically exact in the limit of large distance. So deriving this low energy effective theory systematically from microscopic model is called linearization group. The modern framework was basically developed by Ken Wilson, which is very powerful and nice concept. But if you have ever tried to do this, you know that actually deriving this using RG is usually very difficult and hard. So often what you do is to guess what would be the low energy effective theory, and then try to predict something from this low energy effective theory against the experimental result, numerics, and so on. But in this context, what can be very useful is to derive the universal constraint, which holds independently of the microscopic details of the model, just depending on the symmetry and general property of the model. And this kind of universal constraints are useful to test your theory. You have candidate low energy effective theory, but it has to be consistent with this constraint. And also this kind of constraint can be useful as a guiding principle, where to look for interesting phenomena and so on. And indeed, this kind of universal constraint can be often derived by doing a simple thought experiment. So I guess I'm supposed to speak at least a little bit on behalf of this Ultra Quantum Matter workshop, which started this week in Aspen. And there's some agenda. And so at least part of agenda is about the understand the fractionalization in correlated materials and engineer this fractionalization and so on, blah, blah, blah. So this fractionalization is one of the main topics in this workshop and generally in our field. So what is fractionalization? So this is one of the most intriguing phenomena in quantum condensed matter or ultra quantum matter. And so it means following. So in condensed matter, like a solid, made of atoms. And the atoms are made of protons and neutrons and electrons and so on. And yeah, we can call them as elementary particles. So maybe I would call them as constituent particles, because those particles are often what appear in my microscopic model. And usually, well, at least in condensed matter, these constituent particles, microscopic building block of our condensed matter, has electric charge, which is only integral multiple of elementary charge E. There is no 1/3 charge of E in microscopic world. In some quark have 1/3 charge, but we are not in this energy. Okay, so we always have this constituent microscopic particle have a integer multiple of unit charge E. But in some systems, we found some quasar particles which has fractional charge. So, for example, 1/3 of E. And this is not well. So if you see this kind of fractional charge, you might think this is what you get by breaking electron into 3 pieces or something. If you hit electron hard enough, then maybe you can break electron into single electron into 3 pieces. Then each piece would carry 1/3 charge. But that is not happening, at least in condensed matter, because at least in our experimentally accessible regime, electron has been always point particle, so you cannot really break electron into several pieces. But still in condensed matter, we can find 1/3 E charged kind of particles. And in fact, those are fractionalized quasar particles carry fractional charge, but those are not broken piece of electron, but rather collective excitation involving many, many electrons. And somehow, collective motion of many electrons from distance look like some single particle-like excitation, which somehow carries 1/3 charge. And this was first theoretically demonstrated for fractional quantum Hall state in Laflin wave function by Laflin himself. But as the agenda for this workshop states, we are discussing many other potential realization at zero magnetic field and in ordinary materials and so on. So this is a very interesting example. And in this talk, I'm not going to discuss this Laflin state and so on, how this can appear in many body physics, but rather discuss what happens if this kind of fractionalized quasar particle is realized. Then there are consequences. So for a purpose, let's assume that fractionalization happens. You have some fractionalized charge excitation, quasar particle excitation. And we make several assumptions, which are kind of reasonable. So most important assumption is that your system has a gap. So you have a ground state, and all the excited states are separated from ground state by non-zero energy, which is a gap. So you need to give the system some minimal amount of energy to make any excitation. That's one of the basic assumption. Of course, the system is made of the constituent particles like electron, which has only the integer charge. But somehow, as a collective excitation, this fractionally charged quasar particle appear. That's the assumption. Then let's see what are the consequences. And another assumption I'm making is that once you create quasar particle Hall excitation, you can pair annihilate or pair create, also move them freely. So it's like a particle, really like a particle-like excitation, which I assume. Then I'm introducing two kind of hypothetical process in my head. So I assume that from the ground state, you can give some energy and make a quasi-particle Hall pair creation, a particle Hall pair, that's a pair creation. And I suppose that you can drag this quasi-particle freely. Let's drag my quasi-particle to x direction. And assume that the system is on torus. So if you keep dragging my quasi-particle to the plus x direction, eventually the quasi-particle comes back to the original location. And you can pair annihilate quasi-particle Hall. You should go back to the ground state, vacuum in field theory terminology. So we can introduce this kind of process, at least hypothetically. And I would call this process as Tx. And this process can be, at least in principle, defined as unitary time evolution, because you have some Hamiltonian, you introduce some extra potential or something, and excite this quasi-particle pair excitation, and drag the quasi-particle by moving potential or something like that. So it's very complicated, but this Tx should be defined as a unitary operator, which maps the ground state back to the ground state. And then I also introduce another hypothetical process. That is, I define the system on torus, so there is a hole. I can introduce a magnetic field. And I can consider the adiabatic insertion of the magnetic field. And the magnetic field inside the hole can be represented by vector potential in the system in x direction, Ax. Initially, there was no flux, so vector potential is 0. But I introduce vector potential in x direction and increase this vector potential x diabatically very slowly. And finally, when flux enclosed by this hole, which is a unit flux quantum, h over e in SI unit. But if we take the natural unit, h bar equals to e equals to 1, then this is just 2 pi. So I call this unit flux quantum. And so my fx is the adiabatic insertion of the unit flux quantum. So adiabatically increase the vector potential from 0 to phi 0 over Lx. So I would call this fx. And now I have introduced two sets of operations. But now, okay, so I have previously introduced this Tx, but you can do the same process with 0 flux or 2 pi flux. And okay, so I introduced this. I introduced the notion of the unit flux quantum phi 0. But what does it mean? So it's related to the famous Aharonov-Bohm effect, because in my setup, magnetic flux is confined within the hole of the torus, but my electrons or particles are moving around the surface of the torus. So the particles don't feel the magnetic field directly. So there is no Lorentz force. So in classical mechanics, because there is no Lorentz force, this magnetic flux or magnetic field within the hole shouldn't affect the motion of particles at all. But quantum mechanically, this magnetic flux does affect the motion of electrons, particles on the torus, because of the Aharonov-Bohm effect. That is, in quantum mechanics, electrons can travel clockwise or counterclockwise, and you need to consider superposition of all possible paths. And in the presence of magnetic flux, exactly this flux gives the phase difference between this clockwise motion and the counterclockwise motion. So when phi is non-zero, you change the pattern of interference of electron traveling clockwise or counterclockwise. So you change the motion of electron quantum mechanically. So this is nothing but the Aharonov effect. But there is one important exception. That is this phi gives a phase difference between two paths. And when phi equals to 2 pi times integer, then phase difference becomes 2 pi times integer. But you cannot detect the phase difference of 2 pi or 2 pi times integer. That means that when this phi is 2 pi or its integral multiples, and there is no Aharonov effect. Aharonov effect happens only when phi is not 0 modulo 2 pi. So in that sense, for particles living on torus, having 0 flux is completely equivalent to 2 pi flux. Although Hamiltonian is different, because for 0 flux, vector potential is 0, and 2 pi flux, you have non-zero vector potential. So Hamiltonians are different, but physically, for particles on the torus, they should be equivalent. In fact, such an equivalence can be formulated mathematically using the notion of so-called large gauge transformation, which is not a very good naming, in my opinion, but okay, this is the standard terminology. So gauge transformation is nothing but the local phase transformation of wave function. So you change the wave function by some phase factor e to I theta of r, and theta of r is some generic function of location r. This is a general gauge transformation. But in order to eliminate this 2 pi flux, we should take this theta phase factor as proportional to x. And if you go around the system moving to x direction, x increases from 0 to Lx, and this phase changes from 0 to 2 pi. So theta itself does not satisfy the periodic boundary condition, but the phase factor obeys the periodic boundary condition. So this kind of gauge transformation, which is topologically non-trivial, and which is called large gauge transformation, is completely compatible with periodic boundary condition. So actually, you can write down the explicit formula for large gauge transformation. For example, on lattice model, it looks like this. And using this large gauge transformation operator, actually Hamiltonian at 0 flux is transformed to Hamiltonian at flux 2 pi. So this physical equivalence between 0 flux and 2 pi flux is nothing but this gauge transformation of the Hamiltonian. Okay, now I go back to my problem of system which I assume the fractionalization happens. I assume that there is some fractionalized quasi-particle. Then in this case, so let's consider 2 pi flux, unit flux quantum through the hole, and consider this process Tx, where I create a quasi-particle hole pair, drag quasi-particle to x direction, and go around the system once, and then pair annihilate. Okay. So as I said, unit flux quantum 2 pi is exactly defined such that electrons don't have the Aharonov effect, because phase gain is 2 pi. But this phase gain is actually proportional to the electric charge of the particle. So if I create a quasi-particle and drag this quasi-particle around the system and make one round, then the phase, quantum mechanical phase picked up by this quasi-particle is actually this fractional charge P over Q times 2 pi. So you get the non-trivial phase. Exactly because of this fractional charge of my quasi-particle. So this can be represented in this commutation relation. That is, if you do this quasi-particle creation and dragging and annihilation before flux insertion or after the flux insertion, you get the non-trivial phase to 2 pi I times P over Q. P over Q is some fraction, non-trivial fraction, which represents a fractional charge. Okay. Okay, so this is very suggestive, but this doesn't yet give us any constraint because Tx in the presence of zero vector potential is different from Tx in the presence of 2 pi flux. But now we can invoke this large gauge invariance because now I have to use the knowledge that my microscopic model consists of electron with charge E. And there is no microscopic particles with a fraction charge. Then, fully Hamiltonian in the presence of 2 pi flux is a large gauge transformation of Hamiltonian with zero flux. And this Tx process, creation of quasi-particle where the dragging and the pair narration should be presented by some unitary time evolution using the time-dependent Hamiltonian. So that means that it's my process Tx in the presence of background, well, in the presence of 2 pi flux is nothing but a large gauge transformation of Tx in the presence of zero flux. Here I'm using the knowledge that my microscopic model consists only of electrons with charge E. Then if I use this, then my relation, non-trivial phase picked up by fraction charge relation can be rewritten as this, where this F tilde is a combined operator, which means that you insert a 2 pi flux diabatically, you get a vector potential, but then you can eliminate this vector potential by Ux. So this is a adiabatic flux insertion, and you eliminate the gauge potential, vector potential by large gauge transformation. So I can now define this F tilde, and we can easily see that Tx at zero flux has some non-trivial commutation relation with F tilde x. And both Tx and F tilde should map ground state to ground state. Okay. But they have this non-trivial commutation relation, which means that you cannot have single ground state. So if you have a gap, then the ground state must be degenerate. Actually, we can easily show that for this U over Q with P and Q coprimes, there must be Q degenerate ground state. So in this way, fractionalization is shown to imply the ground state degeneracy on torus. And it doesn't stop at the torus, because we can imagine defining the system on more complicated topology. So for 3D system, we can consider manifold is genus G. Genus is, roughly speaking, number of holes in this kind of picture. So for example, this double torus has 2 holes, so it has genus G. So for this kind of higher genus manifold, we can apply the same argument for basically for every hole. So we can drag the particle around this hole and insert flux in this hole, and likewise for this hole, and so on and so on. Yeah. Yeah.
Now, if I find that I have a degenerate ground state, now you show that you have fractionalization, you have a degenerate ground state. Yeah. Is the other way also correct? That if you have a degenerate ground state, they can always find fractionalization?
No, yeah, because the degeneracy itself only, degeneracy can be result of spontaneous symmetry breaking. In that case, there is no fractionalization. But maybe we can show, we can assume the existence of topological degeneracy. Maybe, but I don't know how to prove. Yeah, as far as I know, there is no reverse statement. Yeah, one way. Yeah, truth within my knowledge. So anyway, so if you have higher genus manifold with many holes, then you can repeat the argument for each hole. Then you can show that the ground state degeneracy of the system on this kind of manifold is at least q to the power of genus G, which means that the ground state degeneracy increases as you go to higher genus manifold. So this is signature of so-called topological degeneracy, which is distinct from the usual degeneracy coming from the ordinary standard spontaneous symmetry breaking. Because for example, for Ising model, if you have long range order spontaneous symmetry breaking, you can have two ground state degeneracy corresponding to upspin and downspin. But it doesn't increase this degeneracy for Ising spontaneous symmetry breaking doesn't increase for higher genus. But once you assume this fractionalization, ground state degeneracy increase like this. So this is thought to be a signature of so-called topological order. So this thought experiment, simple thought experiment, implies that in order to have fractionalization, in my sense, a system must have topological order. That's a strong statement, I would say.
Maybe it's the same question as Aspen, but presumably you can have topological order without fractionalization.
Yeah. So, but yeah, I don't know. Of course,
Toward all bosons, costless, Thouless, transfusion topological order.
that's the different sense, I think. The Kosaris-Thouless transition, maybe we can call Kosaris-Thouless a topological transition, but not in this sense, within my knowledge. Maybe we can discuss later. Okay. So this is one application, and I'm running out of time, but let me discuss another application of the same setting, flux insertion, or translation-invariant system. So yeah, in the previous discussion of fluxization, I didn't have to assume translation invariance or anything. But now I'm considering the translation invariant system. In condensed matter and also cold atoms, often we don't have continuous symmetry because we have some lattice model or crystal background. But we can consider this kind of Hubbard type lattice model, which has a discrete translation symmetry, lattice translation symmetry. And typically Hamiltonian is given by like this. And now that we have translation invariance, we can discuss also momentum and also flux insertion. Again, the same flux insertion. So we can insert a flux, magnetic flux in the whole system. And initially phi was 0, and increase phi up to unit flux quantum 2 pi. But what I didn't discuss previously is that even in classical electromagnetism, increasing phi means that you induce the electric field along x-axis. This flux insertion actually physically induces electric field in x direction. And now, because we have translation invariance, we can define the total momentum of the system. So I want to discuss what happens to the total momentum of the system. But in the presence of, okay, so in my system, already here I'm considering lattice system, so it doesn't have continuous translation symmetry, but it has a lattice translation. And total momentum generally can be defined this way. So Tx is the operator which shifts everything by one lattice side to x direction. Then total momentum in x direction, Px, is related to this translation operator. So Tx is exponential of Ipx. This is a finite distance version of the momentum is nothing but a generator of infinitesimal translation in continuous space, but in lattice, it looks like this. Then important point is that by definition, this total momentum in this lattice is only defined modulo 2 pi. Because if you change Px by 2 pi, Tx doesn't change. And of course, this is very well known in solid state physics. That's a Brillouin zone. The momentum change by 2 pi is equivalent to 0. Okay. And now I want to discuss flux insertion. So I want to couple the system to the vector potential. And that was done by replacing this kind of hopping term. Hopping term is phase factor coming from the vector potential. And for this flux insertion process, I can choose Ax as just a flux phi divided by system size in x direction Lx. And the important point is that in this choice, uniform gauge Ax is uniform everywhere. It doesn't depend on location. And that immediately implies that I Hamiltonian with any value of flux, any value of flux or value of uniform Ax is translation invariant. So it commutes with the translation operator in x direction. But Tx was related to total momentum like that. So if you write down the Heisenberg equation motion for total momentum px and time evolution of px, dpx over dt, which is given by this commutator with 0. So this implies that the momentum doesn't change under this flux insertion. But this sounds a bit strange because I just reminded you that flux insertion induces electric field. My particles, let's say electrons, have electric charge. They feel electric field, so they must be accelerated by electric field. But this simple and exact and rigorous statement shows that the momentum doesn't change. The electrons should be accelerated. So it looks like a contradiction, but of course it's not real contradiction because resolution is that the px I just defined in terms of translation operator is basically so-called canonical momentum. In continuous space, it's a minus IH bar EDX. So it's gauge dependent. So in the initial state and final state, flux are 0 and 2 pi, which are physically equivalent situation for electrons on torus, as I emphasized. But the background gauge field vector potential is different between this initial state and final state, which means that you are in different gauge. So this px is a gauge dependent quantity. So if you compare the value of px directly between initial state and final state, it doesn't make physical sense because you are in the different gauge. So what you can do is that you insert a flux, and afterwards you have 2 pi flux, but you can eliminate this background vector potential by large gauge transformation. And you get back to the original gauge. After doing that, you can compare final momentum with initial momentum. So let's do that. So to summarize, so we start from initial state, which can be anything, but let's start from ground state. The ground state, I assume, belongs to some total momentum eigenvalue, px0. Then we do flux insertion adiabatically, and adiabatic evolution brings you to some final state, psi 0 prime. But because of the translation invariance, its final state has exactly the same total momentum px0, the initial state. So it seems that there is no acceleration, but as I said, this psi 0 prime is in different gauge. So you need to apply the large gauge transformation to get back to the original gauge. So you apply this large gauge transformation ux to psi 0 prime. I will call this psi prime 0 tilde. And now we can discuss the total momentum of this psi 0 prime tilde, and then compare with the initial state, initial ground state. And this can be done actually exactly using the commutation relation between Tx and Ux. And if you exchange the order, it looks like almost commuting, but it doesn't, because this Tx shift x to x plus 1. As my large gauge transformation involves this x. So if you shift x to x plus 1, you get some difference. And the difference is exactly given by NR. N is a number operator at site R, at every site. And you sum over every lattice site. So this exponential is the phase factor you get by exchanging this order between these two operators, which looks non-trivial. But the important point is that this summation over of NR over order lattice site R is nothing but the total particle number which is conserved. Okay, I didn't say that, but usually it's the particle number is assumed to be conserved. So this is a conserved number. So if I define filling factor nu, which is number of particles per every site, or more generally, number of particles per unit cell, then I can write this phase factor using the filling factor nu. Using this commutation relation, you can easily find that the final state after the large gauge transformation has a momentum, original momentum plus some extra term, momentum shift, which is determined completely by the filling factor u. So there is a momentum shift, which physically corresponds to acceleration of electrons by
That's the
flux insertion.
filling factor of the microscopic part.
Yeah, yes. That's the important part.
Not the emerging.
Right. Yeah. So this is a filling factor of microscopic constituent particles. Okay. So this actually leads to rather strong constraint, especially when this filling fraction is fractional. It's assumed nu is p over q. P and q are coprimes. And the momentum shift is given by this number. And let's say I have a freedom to choose Ly. So I choose Ly to be coprime with q. The total momentum shift is 2 pi times, again, some fraction number, which is non-trivial. Which means that after large gauge transformation, final state has a different momentum from the initial ground state, which means that the final state must be different from initial state. So now, let's suppose that my system is fractional filling, happens to be trivial or featureless insulator without any order or anything. Generically, expect that there is a ground state which is separated from order excited state by the gap, and the ground state is unique if there is no feature at all. But if I apply flux insertion to this system, and this ground state evolves to some state, but if there is a unique ground state with a gap, and by flux insertion, this ground state must end up with the same ground state, same final state as the initial state. But if the filling fraction was fractional, not integer, then final state must be different from initial state because it has different momentum from the initial state. So,
is there a value of the flux where it does go back even for Q over Q that way?
yeah, so
It go back to itself.
so phi I increase from 0 to 2 pi, but the 2 pi flux I can eliminate.
A bit like spin half requiring 4 pi to come back.
It's kind of generalization of that statement. Yeah, as I will discuss later. Yeah. So if I assume the system is a trivial insulator, limit the contradiction. So this scenario is excluded if I just have a fractional filling factor. So fractional filling factor has rather strong constraint. You cannot really have a featureless trivial insulator in this system. So to summarize, if filling factor is fractional, that is no integer, and system cannot be a featureless insulator, then possibilities are system might be gapless, like metals. But you can have a gap. In that case, you must have a ground state agency, which is Q-fold, ground state agency. So this lattice discussion can be only done on torus. So on torus, I have Q-fold ground state agency, which may be due to spontaneous symmetry breaking, charge density wave. But if you can eliminate spontaneous symmetry breaking of usual symmetry, then system must have a topological order. And interesting point is that I discussed this in 2 dimensions for simplicity, but basically this is valid in any dimensions. And also, statistics of the microscopic particle doesn't matter. So it can be for bosons or fermions. So this is maybe generic version of generalized deep matrix theorem. And so intuitively, once you get this result, it's kind of easy, natural to understand, because if you have integer filling, you can easily make a featureless insulator. Because if you have free fermion, you can have a band insulator, which is featureless insulator in some sense. But in order to have band insulator, you have to completely fill integer number of bands, and for that, you must have an integer fill. In the other limit, the strong correlation limit, very strong repulsion between particles, you can put one particle per each at its side. And if these particles cannot move because of interaction, this is trivial, kind of trivial insulator in the atomic limit. And again, this limit, each side has one particle, for example, in this limit. So for integer filling, you can easily make a featureless insulator. If you change filling factor slightly from 1, which means that you introduce extra holes or extra particles. Actually, in condensed matter experiment, solid state experiment, this change of nu is known as doping. You add small number of electron hole. Then, for example, if you introduce hole, small number of hole, they tend to move around freely because this is far from other hole. So if this hole becomes mobile, then system is gapless and kind of gapless conductor. So changing nu slightly from integer tends to make system gapless. So this flux insertion argument kind of confirms this picture and shows that filling-based enforcement is actually robust in the presence of any interaction. Once you see this picture, this deep matrix type of theorem might look trivial. Well, so maybe it's trivial in some sense. You say, yeah, it's natural certainly. But it's only natural or trivial if you get the right picture. And as a historical example, I want to remind you this famous model, one-dimensional spin chain, Heisenberg magnet on one-dimensional chain lattice. So you have spin at every side, one-dimensional chain lattice. Now each spin is interacting with nearest neighbor. Now we can consider this Hamiltonian for any spin S. And for spin 1/2, you can solve this exactly by Bethe that. But for generic spin quantum number, you cannot solve. So the property of this model for spin larger than 1/2 remained rather mystery until 1981 or so. But now I can discuss this model from very general viewpoint because for spin S, the smallest possible eigenvalue of SZ is -S. We can identify SZ equals -S state with vacuum, with no particle at that size. The next available value, S equals to -S plus 1, can interpret this as you put one particle magnon to this side, and so on. So -S plus 2, S equals to -S plus 2 corresponds to you put 2 magnons on this side, and so on. And for this kind of anti-Fermi net, there's some theorem by deep matrix or something. The ground state should belong to total magnetization 0 sector. And magnetization means expectation value of SZ. So if I take an expectation value of SZ, and this magnetization per site in this particle picture is nothing but -S plus nu, where nu is filling factor, particle number per site. So if the ground state has 0 magnetization, m equals 0, then actually filling factor nu must be given by spin quantum number. This means that we can classify quantum spin chains to 2 categories. One with half odd integer spins, spin 1/2, 3/2, 5/2, which corresponds to fractional filling. The other class is integer spin, spin 1, 2, 3, which correspond to integer filling. And we already saw that for integer spins, of course, you can make the system gapless, but very generically, system can just become a featureless gapped insulator type state. Now, indeed, for spin integer, this model develops a gap, whereas spin half of the integer, this model is gapless. This difference we can associate with this filling, and which we can relate to this very general filling enforced constraint. So now you can see this difference as very, very natural, but it wasn't, at least until 1980s, because when Hoden made this famous conjecture, very few people took this seriously. There are many, most people didn't believe, but of course, eventually he was proved right, and he actually got a Nobel Prize, at least in part because of this famous prediction. But now, in this filling view, it's rather natural. But you might call this trivial if you like, but it's only natural or trivial after you get the right picture. That's my point. Okay, so I'm running out of time. So this deep shoot matrix, I wanted to say that so this deep shoot matrix theorem is now very famous, but this original paper in '61, if you look at the actual original paper, the paper was not really about this famous theorem. And this famous theorem was rather put in Appendix B. So apparently, they didn't, authors themselves didn't think this theorem too important. And I guess the reason why they didn't take this too important was that somehow they only proved this theorem for very limited case of spin half. And only after this Hoden conjecture, Fleck and Lee pointed out that this proof works for any half integer spins, but somehow fails for integer, which is consistent with this Hoden gap. But at that time, it was, I think, still mysterious. So, but after that, it was generalized in various ways. But I think this generalization to filling factor made this physical meaning of deep shoot matrix theorem more transparent, because it's difference due to filling, which rather naturally explains difference between half integer and integer spins. So yeah, I had some other applications, but I'm now out of time. So to summarize, so I just discussed this very simple flux insertion type thought experiment. Yeah, there are many other possible thought experiments, but I maybe forgot to mention explicitly, but this type of thought experiment was first used by Laughlin to show the famous quantization of Hall conductivity. But not only that, from this simple thought experiment, we can state that fractionalization requires a topological order, and filling enforced constraint or generalized deep shoot matrix theorem, and a generalized version of Latinger theorem, and even nonlinear frequency sum rule and formula. Sorry, I didn't have time to touch these two, but I hope I convinced you that. So this is simple. Maybe looks rather stupid, but still very surprisingly useful and powerful. And thought experiment, a fun part of theoretical physics. Thank you very much.
Can you explain why this argument to a superconductor? Because the definitely field is completely random. There is a gap, and the ground state, well, there is a degeneracy. In some sense, it's artificial because it's the same state if you have the gauge field in. So can you tell a little bit how you apply?
Yeah, I thought so. Are you considering the superconductor for fractional filling, or independent of filling for superconductor? Whether we can.
Filling can be whatever.
Okay. So, yeah, good question. I forgot, but there's some paper by Hans Hanson and company who claim that even trivial superconductors are topologically ordered. So it's kind of similar argument to this, if I remember correctly. Yeah. So actually, you can show the topological degeneracy even for ordinary superconductor. So it's traditionally superconductors were not discussed in that way, but if you apply similar kind of argument, yeah, even usual superconductors are topologically ordered. Yeah. I forgot the details, but
maybe one relevant concept, the argument as you presented it is using charge constants, like the very phases, relying on V1 symmetry.
If you take now this fractional, emerging fractional excitation, vortex, like to the put angular momentum, this will have fractional orbitals.
Mm-hmm.
Now, if you look at it then on the microscopic picture, there has to be some additional momentum. Where does this momentum come from? Because I said microscopic, it has to be the complete vortex, an integer with a fractional quantipart, because I have in a similar like you had here your linear momentum, but now it's linear momentum.
Yeah, but so it's a usual integer vortex for fractionalized particle as rather integer times unit flux quantum. Am I right? So for microscopic particles, it's to rather multiple vortex.
Yeah.
So so your question is this multiple vortex should carry more momentum or something like
Yeah, but what happens, you didn't this picture here with the linear momentum.
Oh, okay. So okay.
Momentum.
Yeah, good question. So yeah, indeed, for this, idealized torus. So actually, I'm really considering flat dimensional space with theoretical boundary condition, but you can relate this momentum of torus with angular momentum in this setting. Yeah, that's right. Yeah, that. So yeah, actually, at least in some limit, we can identify the angular momentum with this momentum argument. And actually, one indication is that sorry, I skipped, but so if we consider fractionalized Fermi liquids, according to Sentius, Sachev, and Boita, so they have topological vortex excitation, and if you apply this momentum counting argument, then if you insert a flux, you somehow automatically create this fictional hypothetical topological vortex in the hole, which carries angular momentum, which is translated to this momentum on torus, which has some contribution to the total momentum, which changes the volume of the Fermi sea. So yeah, I think generally your observation holds.
So is it always unambiguous where you start counting from, what the vacuum is relative to counting charge? Because if you counted somewhere other than the vacuum, you would get the wrong counting of whether you're fractional or integer charge, right? How do I know that, like, the all down state is where I should start counting?
Your question is whether the initial state has.
Yeah, I mean, so in the Heisenberg example, you started counting charge. 0 being all dead.
Okay. Yeah.
It seems like it's a bit arbitrary where I start.
Yeah. But it doesn't depend. I believe. Yeah. At least in if I count a filling with respect to microscopic particles, there's ambiguity.
Oh, I see.
Changing the you can regard minus S as a vacuum, but you can also regard plus S as a vacuum.
What about
So-
0?
Yeah, that's, but I think the point is that for half integer spin system, yeah, there is no middle. So for spin 1/2, S equals to -1/2 or +1/2. You can regard either of them as a vacuum, but you cannot take middle because there is no microscopic. Yeah, but if you identify any microscopic state as a reference vacuum, I think the final result should be the same. Yeah, thank you.
I mean, the original derivation then look at the sigma model with the topological term, which present or not present depending on the single half or one. On the other hand, you have this large, and how can you connect these two things?
They must be related, although yeah, that's a kind of long-standing question. Yeah, so this topological term argument is of course very nice, but it's limited to the system with SU2 symmetry, more restrictive. There is some relation between this and that. But let's see. Yeah, of course they are consistent. But yeah, it's not too obvious to make a direct connection between these two, but they are consistent.
I think you have 2 more questions, and then we.
Oh.
How do you think about these Billian constraint type anomalies in relation to like drift anomalies? Are they special to systems with translation, or can you have other?
Yeah, so okay. Probably you are more expert on this than me, but so I didn't mention. But I think so I didn't have time to mention. But yeah, in field theory community, now this deep shoot matrix theorem is regarded as a consequence of so-called two-fold anomaly. In particular, this is kind of mixed anomaly between U1 and translation, and actually this kind of signifies the anomaly. So you can gauge this U1 symmetry by inserting the flux, but this doesn't commute with translation. And this non-commutativity between the translation symmetry and the unit flux quantum insertion corresponds to mixed two-fold anomaly in field theory. That's my understanding.
But usually it doesn't depend on the symmetry factor, right? It's just, or Tufte anomaly is just the algebra of the operators. It doesn't, here it depends on the symmetry factor.
Oh, yeah. Right. Okay. Maybe somebody knows about this better than me, but somehow in order to discuss this in field theory, somehow we need to fix the symmetry sector in microscopic model. That's my very rough observation. Yeah. So once you have effective field theory, this translation symmetry often acts as a kind of internal symmetry. It doesn't commute with this gauging of U1. So, yeah, sorry, I don't have really direct answer to your question, but my observation or feeling is that somehow in order to discuss this kind of stuff in field theory, you need to fix the symmetry sector first. Maybe I'm wrong.
Thank you.